Hello and good afternoon. Welcome everybody out there from Vienna. My name is Stefan Komornyik and I'm managing partner at HAKOM Time Series. And I'm here together with our experts, Heinz, Alexey, and Georg from QMware. Hi.
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 Hello.
Last time we talked about the backbone of the data-driven energy sector, and the feedback was truly overwhelming, as for the first time we had more than 150 participants, and I can see again, more than 100 today. So that's really great, and we took this as a motivation to find once more a real trendy topic. So therefore, we will now take a look at the quantum computing advantage for time series processing today. In 30 years' work for the energy sector, our focus is and has always been on time series, and we regard them as the elementary particles of the energy sector. With a constantly growing base of more than 100 companies in over 15 countries already using our time series technology, it's our mission to make energy data valuable. So now, first of all, let me introduce QMware. QMware is a joint venture of two companies that have an impressive know-how in high-performance computing on one hand and quantum technology at the same time. They offer the first global quantum cloud, providing services from analysis, proof of solution, implementation to training and support. Their virtual quantum machines make it possible already today to develop and run quantum algorithms for really complex tasks. And that's exactly what we asked them to do with a time series-based use case. And today they will share their results with us. So I'm especially proud to welcome their CTO and co-founder, Georg Gesek. Hi, Georg.
Hi.
Their business development manager, Heinz Popovic. Hi, Heinz.
Hello.
And Alexey Melnikov, their head of the quantum machine learning group at Terra Quantum. Hi, Alexey.
Hello.
Heinz will share some general thoughts on hybrid quantum computing, and Alexey will then introduce the use case. Together with Georg, they will be available for the Q&A session right at the end. But before Heinz takes over, let me start with some general considerations about why we should deal with quantum computing already today. And in the meantime, please do not hesitate to ask your questions in the Q&A function. But why quantum computing? Why should we care about that today? You might say that there are no useful quantum computers around. But do you know Edgar Dijkstra? He was a Dutch mathematician who developed an algorithm for finding the shortest way from A to B. And it is the basis for every navigation system we use today in our cars. And he developed this algorithm for Turing machines. Those are the computers that we use today. And do you know what? He did that at a time when there was no such a machine available, not a single one. So there's a strong point in dealing with technologies as soon as you know that they will soon be available. And we are in a much better position today regarding quantum computing. The quantum cloud service is already there and it's ready to use. But what are the use cases? In our last webinar, we talked about the data processing challenge in the energy sector. We called it the energy data jungle with many different data sources, storages, and as you can see at the bottom, the various applications. Most of those applications depend on data coming in from many different sources, and some need to be processed in near real time. Positioning our time series technology in the middle and harmonizing and validating the data will make it much easier to handle complex use cases. And many of those are use cases for applied machine learning. One of those use cases we chose for today: forecasting energy production from renewables very quickly in order to determine your new market position. And there are loads of other use cases that demand for speed and precision at the same time. If you just think of optimization and risk management, and that's where quantum computing comes in. Why quantum computers have the power of tackling exponentially growing problems. And why is that? Simply because they allow for exponentially growing parallel computation powers. Using qubits instead of bits will do the job. Alexey will explain a little bit more about that later. But first of all, I ask Heinz to tell us more about how QMware's hybrid quantum computing works. So Heinz, please jump in.
Thanks, Stefan, for the introduction. How do we do quantum computing? We do it by mixing the logic of classical bit-based computing, meaning using classical gates with two states, alongside with qubit-based computing in a singular computer. Thus, we program classical computer algorithms and quantum algorithms and combine them in our memory-centric machines that virtualizes the classical and the quantum processor for the user. Quantum algorithm design is still very specific, and the knowledge you need is very, very specific, and not too many people know about that. at the moment. This is why we take care of this development for our customers. It is also very important, as well as there are still limited number of qubits available. Therefore, in order to gain from quantum computing today, we have to spend reasonable amount of knowledge to build the best suited quantum algorithms. We have a team of about 80 very advanced quantum algorithm specialists in our team at Terra Quantum today. Here you see the structure of our framework and the software stack that we developed for our hybrid quantum computers. It consists of the kernel extensions for virtualizing the classical and the quantum processing, the development SDK with Python and C++ capabilities. Our framework is called BASIC with a Q at the end. The important message for our customers is all you develop and run now is future compatible. As we virtualize the hardware layer, it will be compatible with all the coming physical quantum processors as they become available for day-to-day use in the future. The second part of our offering is the hardware side. We have our HQC 4020, that is a memory-centric machine made out of 8 modules, running 12 terabytes or more of RAM, and it enables us today to have 40 error-free virtual qubits for real-life applications. This machine is available on premise or in our hybrid quantum cloud. As this machine is a hybrid quantum and classical computer, it can run the HAKOM ESM software as well and directly connect the data for the quantum-based calculations. With our quantum IT technology, we can solve many different use cases, from optimization to simulation and many more today. One very interesting technology is quantum machine learning, and we are proud to have Alexey Melnikov explaining to us today more about quantum machine learning using our technology and based on the HAKOM time series data for the energy sector. Dear Alex, please take over and share your presentation.
Thank you, Heinz. Thank you, Stefan. For the next 10 to 15 minutes, I will explain how we use quantum machine learning for photovoltaic power forecasting. But before I jump to the use case and show our results, let me introduce you the topic of quantum machine learning and educate you what it is. To do this, I chose a simple route. And for that, let us think for a while about machine learning algorithms that can be viewed as a black box, which you can see on the slide. This black box takes an input. For instance, this would be a time series and outputs a forecast. If we look inside such a black box, we would see that it can look like as a parameterized function f, which takes inputs, model parameters, and produces an output. A quantum machine learning also can be thought of a black box model, but it's a quantum black box model. So this quantum black box model also produces parameterized functions, but of a different type, and I denote this type as Q functions. This Q functions also takes inputs, model parameters, and produces outputs. But these functions, as I will tell you later, can lead to better forecast accuracy, can lead to better forecast speeds. And the question is, what's specific about this box? What makes it quantum? What's inside of this box? And of course, the answer is there is a Schrödinger cat inside the box. You can see it on the picture, and this Schrödinger cat is very peculiar because it can be in 2 states at the same time. It can be both dead and alive at the same time. This can be represented as a sum over different states with a coefficient alpha 1, it's alive, and with the coefficient alpha 2, it's dead. But in this talk, we will, as promised, not talk only about Schrödinger cats, but we'll go to quantum information. And we now talk about qubits. Qubits are very similar quantum objects in the sense that they can also be in two different states at the same time. For instance, a single qubit is a sum of two states, bit 0 and B1, with different coefficients, alpha 1 and alpha 2. The things become much more interesting when we consider more qubits. For instance, if we take two qubits, Q1, Q2, then it's a sum of four terms. Term with of 0, 0 bits, 0, 1, 1, 0, and 1, 1. If we go to three qubits, this would be a term alpha 1, 0, 0, 0, then alpha 2, 0, 0, 1, then 0, 1, 0, and so on until 1, 1, 1. If I go now to 40 qubits, the amount of qubits that we can represent on our hybrid quantum computer, then we would see that it can represent more than 1 trillion terms in one quantum state. So that gives you a rough idea that 40 qubits is not just a small number. It can represent more than 1 trillion complex numbers. So the question is, how would we use this large capacity available in quantum information? We can use these encodings to construct new families of functions for machine learning. They would be executed fast on quantum devices. And we know for sure that it's impossible to efficiently reconstruct these functions on any classical machine if the number of qubits is large enough. These functions would have better regularization properties as indicated by our experiments. And we have a possibility to observe qualitatively different machine learning models by that. One peculiar thing about this quantum machine learning models is that we can compute distances between vectors exponentially faster. The picture on the right shows the intuitive picture what's going on with quantum machine learning models. We feed information in our input space represented with this cloud with vectors x1 and x2. And then these data points, they are moved to exponentially larger quantum feature space with these functions phi of x1 and phi of x2. And then in this bigger cloud, exponentially larger cloud, we do quantum computing operations. We compute distances between vectors. We do some classification with our models. And once we are done, we return back to the output space with the exponentially, which is exponentially smaller. And then we achieve these Q functions, which I talked about. These functions lead to new families of machine learning models. These are hybrid neural networks architecture and quantum-inspired machine learning models, which I will use later. So let's now be more concrete. So now on the left, you see a concrete quantum neural network layer, which contains 3 qubits, and they are manipulated with quantum gates. So you see that the input vector, our X vector, is applied to perform a quantum feature map on the state of qubits. Then we would have our quantum variational model, which is a parametrized model, which we will do with a gradient descent. We will change these parameters. And then we do a measurement. After the measurement, we collapse, we move back to our exponentially smaller space to reconstruct the output. So if you are not familiar with this quantum neural network layers, there's absolutely no problem because the picture on the right shows exactly the same model. So we have input vector X, which can be encoded into 3 neurons. Then with a nonlinear encoding, we map the state of neurons into an exponentially larger layer of neurons. It would be a fully connected layer of neurons parameterized by weights theta, which are the same thetas as you see on the left. And then we do, after we have this fully connected layer, we do a nonlinear decoding, outputting information into three neurons like that. So the core of this model is right in the middle. So it's this fully connected layer of neurons, which has exponentially large capacity, which can be simulated with linear number of qubits, but needs exponentially large number of bits to be simulated. So we now use this capacity and use our expertise to apply quantum machine learning to photovoltaic power forecast. We will forecast the produced photovoltaic power based on the present and the past values of power, meteorological parameters such as air temperature and solar irradiance. So this is our data set. In our data set, we use hourly mean ambient temperatures, hourly mean module temperatures, hourly mean solar irradiances measured on 2 tilted planes, hourly mean photovoltaic power for a period of 21 months. We break this data set into training, testing set, and taking the data from the last 24 hours, we predict what would happen in the next hour. So this is a test bed for our quantum machine learning techniques to check and show what are the benefits of using hybrid quantum classical machine learning models. So usually one would use traditional methods for machine learning, such as artificial neural networks, support vector machines, or variants of support vector machines, convolutional neural networks, or recurrent neural networks. In our case, we applied quantum convolutional layers, and we applied first fully connected quantum layers and combined it with artificial neural networks. So we feed our test data, we feed our training data. It goes through the combination of artificial neural network and our quantum neural network layers, and the output would be prediction on the power generated by the photovoltaic unit. We also try other approaches, such as replacing artificial neural networks with quantum convolutional layers, which is a more advanced way to process information with quantum systems. So let me jump now to the results. On the left, you see a representation of classical artificial neural network, layer by layer, and close to it, on the right, there's a hybrid quantum classical neural network representation. You see the only difference is that we have now a quantum layer instead of a classical layer in one place. And the structure of this layer is exactly the same as I described on a couple of slides before. So if you're interested, you can try reproducing the results that I show you now. So the results are the following. On the top, you see how classical and hybrid quantum classical models predicted a future power generation for the next 60-something hours. And we can compare it to the real data captured afterwards. We see the shape is similar and the models look maybe similar. But if we go deeper into the details and look what are the mean absolute errors we observed during the learning on our test sets, then we see at the bottom that the hybrid model outperforms classical model. So we see that the error goes below 5% for the quantum classical model, and it stays at around 6% for the classical model. So these results are obtained after 10 individual runs. So this is the average performance both for classical and for hybrid models. And here you can clearly see the separation which is brought by a single change in the neural network layer. We replace classical with quantum, and that's it. So this result brings me to the summary. I showed you that quantum machine learning gives us new tools to process data. It gives us new family of hybrid quantum machine learning algorithms that can lead potentially to better performance in forecast accuracy and to better forecast speeds. With our use case, applying quantum machine learning to forecast power generation, we observe that hybrid quantum classical neural network gives us quantitatively better forecasts. We see a separation in the error on the test set, which is better for hybrid quantum classical models. We see that the hybrid model has an advantage of quantum encoding for faster forecasting, and it can capture exponentially more correlations between predictors. And our ideal goal is shown on the right. You see, if the time series window would grow, classical model would need exponentially more time to forecast correctly. But the goal is that with quantum model, we try to stay on the linear scaling. That's the goal, and we would work on it further to demonstrate the scaling. But also, we have other use cases, and we can apply machine learning for instance, risk management, trading, and many more. And here's a picture that Heinz discussed, the hybrid quantum HPC, on which we already run our hybrid quantum classical models. Thank you.
Thanks, Alexey. I will take over the screen again. So as we can see, the quantum computing advantage for use cases like this is on on one hand speed, but it can also be precision at the same time. And anyway, with speed comes more precision anyway if you have a limited time for computing. So very interesting. I see there are already questions coming in. Please continue. But first, there's one call to action to all of you. Today, we ask you to join us for a half-day workshop in the Quantum Cloud at a very reasonable price, as you can see. We'd like you to share with us your challenging time series-driven use cases for machine learning. We will study it in advance and have a half-day workshop together with you, presenting our results and finding out how the quantum advantage could be useful for your particular challenges. So if you're interested, please send a short message to tsmlab@hakom.at or use the chat function, and we will contact you later on for the details. So now let's start with the Q&A session. Well, I have several questions there. Maybe we start with one. Are there already ready-made machine learning frameworks that contain quantum layers, or did you have to implement everything yourselves? That one goes to Alexey, I guess.
Yes, thank you. Good question. So we have implemented it ourselves. So we have our own framework implemented for the QMware machines, for the hybrid machines, but there are other frameworks like TensorFlow Quantum, or Qiskit, or PennyLane.
Okay, thank you. Why quantum machine learning should outperform classical ML methods? It's a general result, or only a particular case that the one shown in which it seems that the test sample could be very similar to train one? Maybe Alexey, would you like to?
So yes, I would be happy to respond. Yes, so we don't know in advance that, of course, for all data sets, the quantum machine would outperform it. It would be a false statement, but we have a certain intuition and certain understanding in which settings quantum machine learning is much superior because of this construction that I demonstrated to you, mapping from a small space to a much larger space and do much simpler classification in this space. If we do it correctly, this could bring us both speed and accuracy.
Okay, thanks, Alexey. Thank you. I think to Georg, a more general one. How fast do you expect quantum computers to be available for operational purposes?
Yeah, this is a very good question and very differently answered in the community. Our answer is today we have a hybrid quantum computing system. Hybrid means it's a high-performance computing system together with virtual quantum processors. Virtual means there is a simulation behind, but the application is not aware of. So as soon as data center grade ready quantum processors are available, we can fit them into our hardware platform, and your application will additionally gain speed up without reprogramming it. And what we see very interestingly is that our virtual quantum processors, because of the very different algorithmic and compute paradigm, are outperforming classical HPCs by some extent, not exponentially, of course, but by quadratic or something like this speed in certain use cases, as Alexey mentioned. So quantum computing can bring you an quantum advantage today with QMware.
Thanks, Georg, for this comprehensive answer. Another one. How do you address the decoherence problem? Is that one for Alexey?
So for now, we use the hybrid machines which do not suffer from the decoherence process. So we have ideal logical virtual qubits. So we don't have this, but it's a good question. So once we work with native QPUs, quantum processing units, we would have inevitably decoherence. And it's an interesting question whether the models that I showed you survive under this decoherence. And the positive indication that it adds just a bit of noise into a machine learning model, which is not bad necessarily, because this might make model more robust to some sort of data, but it depends on the data.
Exactly, and I might to add, so machine learning is a very good example where you can deal with certain errors. Decoherence is one of those errors we can also predict in a kind of a machine learned way. So it's machine learning on machine learning in order to mitigate the errors. But there is also very much going on with our technologies on native quantum processors. So we are also working together with Terra Quantum on native quantum processors, which are developed and produced in Europe. And the answer is simple: speed. The faster we can compute quantum gates in an integrated circuit, the more processing steps we can implement before decoherence creates too much error.
Thanks, Phil. Another one. Nice results. Thank you. My question is, how many neurons and qubits did you use? Did you simulate or run on a real quantum computer?
You can check our presentation later. On the last slides, it's shown exactly how many neurons are there in each individual layer of a neural network. It starts with 120 neurons in the first layer and then goes down to 1 at the last layer. We ran this simulations of both classical and hybrid model on our QMware machine, on our hybrid computer, and this involved virtualized qubits. So we simulated all the qubits on high-performance computer.
Thanks, Alexey. Another one. In your model, does only training have to be carried out on the quantum computer, or also inference?
Ideally, you do both on a hybrid quantum computer, but it's not a problem because we have machines available and it can be installed on premise. So it's not a problem. But in principle, once it's trained, one can also think to map it to a fully classical model and pay longer speed of computing the output, still have the same quality of the results.
Okay, thanks, Alexey. Maybe a last one in our official part of the webinar regarding the performance of the hybrid approach. Did this show the reduction of the training loss over 10 runs, or did we see 10 repetitions of cross-validation?
It was 10 repetitions of cross-validation.
Thanks. As usual now, at the end, I would like to mention our next webinar that we planned for September. And once more, we'll talk about important time series related issues with real persons of interest, as you can see, and hope that you will join again. So please stay tuned to us. Have a good start into summer. And do not forget, life is a time series.